Has its own sense of passion, from that button arrow to again that button. Yeah.
Alright, so it's actually my pleasure to introduce Professor Gadadhar Misra, and for quite a few of us in the audience, like GMS faculty members, he's also our teacher. So it's even more pleasure to welcome him to IISER Kolkata. There's also a conference in his honor which starts tomorrow. There are a good list of speakers. Some of you can attend those. But today he's agreed to talk at the Maths Club, and the title is up there. So I welcome you, sir.
Thank you. Yeah, okay. Over the last 30-35 years, I have tried to avoid talking to kids because I am a very confused person, and much of the time what I say usually doesn't make sense, and I like to carry over that confusion to coffee, to midnight chats and so on and so forth, and hopefully make some sense. So I guess this is a talk I thought it will not be very hard to make up, but it turned out to be quite a challenge. It varies from one extreme to another in the sense that I found out in 1960s, like everyone else in Russia, you are supposed to teach high school kids. Most of the very, very well-known and distinguished mathematicians have taught high school kids. So in 1962, Arnold, one of the very distinguished mathematicians, actually taught a one-semester course to high school kids to explain why you cannot solve a general quintic equation. Now, since this is only a talk for an hour and a half, I am not going to emphasize all the time every little thing that actually matters. So, for example, when you say you cannot solve the quintic in general, that means that there are, of course, quintics that you can solve in closed form, but it is just that if you take it in the general form, okay, that you cannot. And then there is this notion of solving in using only basic algebraic operations and roots and so on and so forth. We will come to that. But the story is that Arnold explained this proof, which is distinct from the proof of Galois, which by then was a well-established part of learning mathematics. And this took a semester. And there is a whole book that sort of describes this proof. In that book, starting from the beginning to the end. So while preparing this lecture, I was looking around. Then I found somebody else lecturing somewhere. Now that video is a pretty bad video, but the name of the mathematician is Dror Ben Allah. So he walks in. He says, yesterday one of my students sent me a short proof of the non-existence of the solution of the quintic, and I am so excited that I must share this proof with you. That's what he said. And he promises, although this is a class on Riemannian geometry or something or the other, he interrupts the class. He begins to give this proof. He says it will take no more than 15 minutes, and it will take no more than half the time. Okay, so So he tries to, so he calls it the 15 minutes proof. And although in modern times people don't do this anymore, at the end he is so frustrated. He says the only takeaway from this experience is that drawer is an idiot. That's what he writes in the blackboard. Therefore, I have no hesitation in admitting that I am also an idiot, but that I have said many times, and many of you know. But that is not done very often in modern times. So the 15 minutes proof is actually Arnold's proof. So the proof, which is on the one hand a semester, on the other hand 15 minutes, and then there is everything in between. Okay? So if you go to the YouTube and start looking for this, there are many lectures that tell you how and why you can establish that there is no general equation. So let's begin with some fun. This is again from that Galois thing. Of course, some of you know because it's a math club. This first slide is for fun. I try to jump between being funny, attempting to be funny, and trying to do some math in between. So all of you of course know square root of 2 is not a rational number, but here is something. Apparently if you write square root of 2 in the form p over q with q as the smallest possible denominator that is allowed there, it turns out by manipulating that you can, this I actually did on a scrap piece of paper. You can easily see that sort of gives you that square root of 2 is also 2q minus p over p minus q. But that's an immediate contradiction because p minus q is a smaller denominator than what you find. So again, now comes the fun part of it. Well, if you know square root of 2 is not a rational number, how do you prove that the nth root of 2 is not a rational number either? Okay? I don't know what proof you have in mind, but here is the proof using Fermat's class. 10 years ago you couldn't have come up with this. Okay? So I will not even bother to read it. It's so trivial that so that's what mathematics really is all about. You go from one thing to the other without. Okay. Now, yeah.
Formally, does the second proof actually work? Like, for that proof to work, we need to know that one's proof of Fermat's Master does not invoke the fact that its root of 2 is not irrational.
I think that perhaps you know. Okay.
So that proof actually doesn't.
I mean, that question I won't be able to answer with my personal knowledge, but since this was taken from someone who ought to know, I would assume that he will not give you a supplement. Okay? That is true. Although we will talk about the proof without Galois, here are a couple of quick slides to tell you what it involves to prove that the quintic doesn't have a solution involving basic algebraic operations together with roots. Okay? And so the reason I mentioned square root of 2 before is that there is one thing about these algebraic things. Depending on from where you are looking at them, they are sometimes distinguishable, sometimes they are not distinguishable. So square root of 2 and square root of minus 2, they are of course two different numbers, but they are indistinguishable from the point of view that if you look at any polynomial equation involving or polynomial expression involving square root of 2 and minus square root of 2, you will not be able to tell them apart. So they are in that sense conjugates. And in fact, all of humanity, which was eagerly waiting to discover I, finally when they discovered I, it turns out they did not just discover I, they discovered also minus I. I and minus I, in a similar way, are indistinguishable over reals. Okay? So you cannot separate I and minus I. if you are looking at them over the year period. Okay? That is what is at the heart of doing these field extensions, this, that, and the other, and the Galois theory. So here is a definition. You say PA equal to 0, the same as PB equal to 0, then A and B are conjugate over Q, and similarly if you have complex fields, Pz and Pz prime are conjugate if they are indistinguishable over R. So, but now rather than one number, you can talk about a couple of numbers. This is by the way, as I said, just a glimpse of what the proof of the non-existence of the roots of quintic mean if you were to do it using Galois theory. I'll finish in just another slide. Of course, without providing any details, just to tell you what it takes. And then you say that two tuples are conjugate, provided, again, polynomials with appropriate coefficients don't distinguish them. Now, the symmetric group of a polynomial is defined to be permutations that allow you to move the solutions around. So, the symmetric group of a polynomial is that if you write the distinct solutions of that polynomial, actually all through this, as I said, the question is about non-existence of a solution of a general quintic. So I sort of assume all the time that whenever I am talking about coefficients of a polynomial and solutions of a polynomial, if the solutions happen to be coalescing at some point, that is if there are double solutions at some point, those coefficients and those solutions are connected. Okay? Essentially try to imagine that what you are trying to do in attempting this proof is to understand some kind of a map between the coefficient space of polynomials and the solution space of the polynomials. Okay? So, for example, for the quintic, the coefficient space of polynomial will consist of 5 tuples all the time. Okay? And that's like C5. And then you have unordered tuples which are solutions. So that is the solution space. All possible unordered tuples. But just like in when you do homotopy or this or that, this business about being unordered versus being ordered, I reserve the right to switch back and forth. Whenever convenient, I will think of them as unordered, and whenever convenient, I will think of them as ordered. Because see, what happens is, you want to go move a polynomial from somewhere back to itself. While it is moving, you want to see what happens to the solutions. So this one polynomial that you are moving, you want to give the name to the solutions of that particular polynomial. That's like the base point. At that base point, you think of it as order. Okay? But again, as you know, the coefficients of the polynomial don't really depend on the ordering of the solutions and so on and so forth. So here is a quick definition. The Galois group of a polynomial P is exactly those permutations such that S1, Sk, if these are the solutions of the polynomial and you permute them, then they are conjugate. Okay? Well, distinct solutions of course means what it means. That you already know. So here is another sort of quick sort of matter of terminology, and again I will be a little careless about this terminology, meaning all I need is actually ordinary roots, because much of the time we will be trying to arrive at a contradiction. To arrive at the kind of contradictions that we need, it's enough to look at roots, ordinary roots, but if you take a cube root, fifth root, seventh root, it's even better. Okay? So to say that it can be obtained from rationals, so we say that a complex number is radical if this happens. You can get it from ordinary rational numbers by taking roots, apart from the usual arithmetic operations. There is a big controversy. If any of you after listening to this, go and try to do your own research, you will find that what you have learned so far, the way this theorem is put, is to say that you cannot find a solution using plus minus, multiplication, division, and roots and so on. Now what is being said is that you cannot actually find, you can replace, after all, taking plus minus, multiplication and division means what? You are sort of writing down some kind of a rational expression in terms of your S1, S2, Sn. And then you are adding a root. Okay, you are doing a root of that rational expression, nested root of the expression and so on. So the thing that is being debated, whether this proof is actually better in the sense that compared to Galois theory, it tells you that not just a rational expression, you cannot take a continuous function either. Okay, you cannot make a continuous function of S1, S2, Sn. I mean, the very first thing I want to discuss is to say that if you have a quadratic equation and you want to say that the solutions can be expressed as continuous functions of its coefficients, then you are bound to fail. Now, many of you can close your eyes at this point and imagine why that should be true. Because we already know the formula for the quadratic involves a square root. And the square root is a two-valued function. It cannot be continuous. It's essentially that, although I'll try to waste a lot of your time bugging you about exactly what that means, okay? Perhaps because I don't know what it really means, all right? So, okay, that's what it means to say in roots or whatever. So the quadratic equation has actually this expression. What is the Galois theorem? Well, you have a P which is a polynomial over Q, then P is solvable by radicals if and only the Galois group is solvable. Now, solvable means it's sort of like commutators of commutators that if you keep taking, then it finally ends up becoming a trivial group itself. Okay? So to give away one of the mysteries of what is going on is that when you are looking at the permutation group from 2, 3, 4, you have one problem, and at 5 the group becomes not solvable. Okay? And therefore it fails. So that is the Galois group. But working out all these details, as many people say, takes a whole semester of work. You need to do big extensions, you need to understand Galois groups and various other things of that kind. Okay. So now let's look at this. There are 3 or 4 things that I want you to keep in mind. You want to solve an equation of the type this. This is a nth degree equation with complex coefficients. You know that by Arnold theorem of algebra, which I am not going to go into right now. Of course, again, one of those small things. Here, without loss of generality, I am taking the coefficient of the x to the power n to be equal to 1. That doesn't make any difference. Because I am talking about a degree. Now, the degree will be n only if the coefficient of z to the n was non-zero, and then I just divide by that number. So these are solutions, x1 through Sn, and as I said, I almost always only look at those polynomials whose solutions are distinct. So now, what happens to the solutions if we move the coefficients a little, and what happens the other way around? So, as I told you before, imagine that you have the solution space and you have the coefficient space. Now, you want to wiggle around the coefficients a little bit. You want to see what happens to the solutions. And you want to wiggle around the solutions a little bit. And then you want to see what happens to the coefficients. Now, one way is much easier than the other, because given the solutions, you can write the polynomial like this, and then you immediately see that the coefficients are actually symmetric functions of the solutions, and indeed, as a result, because of the formula, algebraic nature of the formula, you see that the coefficients are continuous functions of the solutions. It is going the other way around. Given the coefficients, finding the solutions, that is the challenge. Okay? Yeah, if the internet was there, I would have demonstrated, but it looks like perhaps it is not there, so I cannot. By moving, what I mean is that this will come up actually afterwards. You have, that is what I meant by saying I have an initial point, like in the, when you do in fundamental groups or something like that. So you have a fixed point, start with a fixed point. And then think of a curve, okay, t going from 0 to 1, and each of these coefficients as functions of that parameter t. So that at t equal to 0, it is the original polynomial that you started with. You understand what I am saying? So that is what I mean. If these functions are continuous functions, you have to begin with only C0 plus C1z plus C2z square and so on, right? Now imagine that these coefficients, instead of being constants, they are continuous functions of some independent parameter t. Right? So at t equal to half, I have one polynomial. At t equal to 1/4, I have one polynomial. At t equal to 1/8, I have another polynomial. Okay? But in such a way that I start with my t equal to 0 gives me where the given polynomial. Okay? And I slowly go up to half or go up to 1 because these coefficients are continuous functions. They sort of give me a family of polynomials continuously varied with the time t. Okay?
We see only that, parameterized by single variable, like one dimensional thing.
Yeah, if you like, this is one way of saying it. If you like, you can parameterize it by n variables, each coefficient you take to be an independent continuous function. I am not doing that. I am just saying take to be one. And similarly, now when you have done that, when you are looking at this family of polynomials, what will happen is that the solutions accordingly will keep changing, right? Because your ordinary initial polynomial had a certain set of solutions. But when you look at t sub half, where it is the polynomial corresponding to t equal to half, you will have a new set of solutions. Okay? If you move the solutions around, as I said, the coefficients will move in a reasonably predictable way because there is a formula which makes them or expresses the coefficients as symmetric functions of the roots or of the solutions, right? Because of this product rule and this rule that you see here, you see that this really doesn't depend on the permutation of S1, S2, Sn, right? This expression doesn't depend on the permutation of S1, S2, Sn. Consequently, when you write the polynomial, those coefficients will also not depend on the permutation of S1, S2, Sn. And therefore, the coefficients expressed as a function of S1, S2, Sn are symmetric. Anything you call it to be symmetric provided it is invariant under the permutation. Okay? So as I have said here, it is going the other way around that one needs to find, that one needs to understand. So for this purpose, it is enough to talk only about two sorts of permutations. There are permutations of all kinds, but permutations are finally made up of transpositions. But here, we will focus on two kinds of permutations. One that is a transposition and the other that is a cycle. Okay? S1 going to S2 going to S3 coming back to S1. Okay? So these are the solutions that move in a cycle. Whereas if you have two solutions, I am talking about a transposition, S1 goes to S2 and then S2 is just so much for terminology. And then now we want to talk about loops and permutations. So you think of these solutions as in C, and if you go back to this and I permute S1, S2, S3, S3 to S1, I can think of this permutation as a path in the space of solutions. Okay? The permutation, the prescription that S1 goes to S2, S2 goes to S3, S3 comes back to S1, I think of it as a path. Okay? And that I can do with any permutation. So, as I have said here, paths are just continuous curves that connect 2 points. We assume that they do not self-intersect and so on. A path that closes, that is, connects a point to itself is called a loop, denoted by gamma. Here is a closed path. Starting from here, it comes back. Here, this path and similarly this path are not closed. S1 goes to S2. It's not a closed path. Whereas this is a closed path, and this will start playing a role soon. One of the important things about groups and things, if Narayanan was around, he would have reminded me that 30 years ago I used to insist on spending hours telling about logarithm, this, that, and the other, and taking roots. You would be surprised that even today, for the last 3 nights, somebody called Adam Purani, with whom I do a lot of discuss a lot of mathematics, we have been stuck with questions exactly like this. Namely, what is the multiplier of representation, which has to, we always thought that you can take the derivative of a function, raise it to some power, and then use it as a equocycle or something. That turns out to hide a lot more than what we thought we know. So anyway, coming back here, all of you, of course, know about taking a root, and when you take a root, if you, in the next slide, I'll write it in polar coordinates and write it exactly. But for now, just focus on this picture. What is happening is that if you go along this circle, in the complex plane, all of you, without any exception, and without my having to tell you anything more, can see that this semicircle actually goes to the full circle under z square. But that's precisely the reason why, if you look at the full circle, it comes back only to a half circle. Well, what is the significance of that? This is going to be a major character in our play, because one of them is a closed loop, whereas the other is not. Okay? So this business of taking roots does not preserve a particular property, namely being closed as a loop. Okay? If you have a closed loop and you are taking a square root, you are not going back to a closed loop anymore. Okay? See, there are some little things. It's not that there are a whole bunch of details that I have tried to put in. I don't know, but this is one of the crucial key ideas. Okay? But if you are doing it for, a k root, and here, of course, not quite by accident, but it is deliberately taken to be 5, the 5th root of unity. Okay? When you are doing the 5th root of unity, what will happen? If you take z, sort of going around a loop that does not involve 0 at all, as you move along, doesn't matter what you do, the roots, the 5th roots of that z will come back to their original position, because in the expression, this expression that you have for z, r, e, I, theta, when you are not going around 0, your e, I, theta doesn't change from the starting position to the return point. Okay? Because you are not involving 0 at all. It's only when you move around 0 that you increase the argument by 2 pi. Otherwise you are doing nothing. Therefore, irrespective of what is happening in between, you always come back to the same set of roots. They remain the same. Whereas if you are running across, running around the origin, then your roots will sort of keep going to their neighbors. You know, that is something that you can check. Zeta 1 goes to zeta 2, zeta 2 goes to zeta 3, zeta 3 goes to zeta 4, zeta 4 goes to zeta 5. Okay? So there is an explanation here. If you like, I can leave these slides. Some of these things, I mean, the picture sort of tells you what is going on rather than explaining it in words. So that's actually the picture. Okay. Now we are going to talk about a little bit more carefully what it means to have a solution. A formula for a solution S of a polynomial equation of the form dz equal to 0, in general, I come back to that point, in general, not just a particular polynomial or 10 polynomials, but in general, is of the form S equal to this, where R is some function of the coefficients C0, Cn minus 1 of P obtained by using this. As I said, you could replace this. So this is a function of C0, C1, Cn minus 1. You can make up any rational function that you like by using this, but you can also make an arbitrary continuous function if you want. Okay? So the claim remains true even if you replace what is being said using this by using a continuous function together with a root. Okay? You do a continuous function, but then you allow yourself to take a root of that continuous function. In the usual old terminology, it is usually called the discriminant. I mean, in the solution for the quadrant, you will see the square root coming in. That is actually the discriminant. So now, therefore, if two or more of these coefficients follow a loop, the function of type R0 also follows a loop. What I mean by that is, suppose there was no square root. Suppose there was no square root at all. And you claim that your solution is of this form. Okay? Then, if the coefficients go around a loop and you have a continuous function, that will be some other loop, right? I mean, you are going around, this will go somewhere, but it will come back to its original position because it's a continuous single valued function. Okay? So that's one thing to keep in mind. So this property of R0 function is not shared by R1 functions. So what do I mean by R? Didn't I explain? R0. Where is R0? No R0? Hierarchy. Yeah. Okay, that's right. Hierarchy. The first one say R0. So this is supposed to be a whole lot of R functions. R is for root. You are trying to find functions that will actually give you a formula. So I want to kind of look at a hierarchy of such functions. And R0 is the simplest one. Does not involve any root, does not involve anything. It's just a continuous function. Or in the older terminology, a function made out of plus minus division and multiplication of S0, S1, S2, Sn minus 1 or Sn. Well, I start with S0, then I go up to Sn minus 1, start with S1, I go up to Sn. I keep making mistakes of this kind all the time. So, okay, these are polynomials or more generally rational functions of the coefficients of the polynomial. So R0 property of R0 functions is not shared by R1 functions obtained from R0 functions by taking roots. So this is why I had shown the square root of G picture before. Now what I want to say is, actually again I mix up terminology a bit. After you are done with R0, you are supposed to say what happens if I take only square root of R0 or functions that are continuous. I am going to say by a R1 type function, R1 type function. I mean you take roots of the R0 kind of function and do other arithmetic. Okay? So sometimes, so the discriminant alone is always just taking you. But then you have to combine it with other things. For example, when you go from square root to the cubic solution, okay, there will be a discriminant. But then that discriminant is a mess and you keep adding, subtracting other things to make up the solution for the cubic. So the point is, here I again want you to pay attention to this. If I only had a R0 function at my disposal, what will happen is that that if I start with a root, I'll end up with a root. Okay? And what I'm going to do, well, this will be written down somewhere along the way in one of the slides. But let me try to be adventurous and tell you what should happen. For example, I am going to claim that a quadratic expression or a quadratic equation in general cannot have a solution of the form R0, C0, C1. Okay? R0, C0, C1. What does it mean? It means that this R0 is a continuous function of C0 and C1. Okay? But I think there is just one picture that should. Yeah. So I'll go back. But you see, what happens is, when you permute the roots, you have the root space. You start from the root S1, go to S2, simultaneously taking S2 to S1. Well, you still have the same set of roots. In the meantime, while you are doing this, what are the coefficients doing? As I told you, coefficients are continuous functions of the roots. So, the coefficients will actually follow a loop. My R0 function, if I name the two roots, so I have to find a formula for the roots, right? So I have two roots. The first root I call R00, the second root I call R01, and what will they do? Well, they are continuous functions of continuous functions. So if these are loops, those will also be loops. But if I am tracking just the S1, what has happened to S1? S1 starting from somewhere, when I stop, what has happened to S1? S1 is not in the same position. But R00 was supposed to track S1. R00 was supposed to be a formula for S1. I am assuming such a formula is there. But if such a formula is there, then it should come back to where it started. Because of the fact that C1 is a loop and this is also a loop. And that's the contradiction that says that the quadratic equation cannot have a solution in just ordinary continuous functions. That is where the big debate is on the internet about the way it is said before, or it used to be said so far, is that you cannot have a solution using plus minus division and whatever. But now people are saying, no, you can't have it with a continuous functioning. Okay? Now, well, here I have tried to explain a little bit. For n equal to 2, the two solutions are permuted using the transposition. That is the relationship between the loops and the permutations. So a transposition is a curve, as I explained before, and the coefficient C0, C1, each, like you saw in the picture, move on some path, but they must come back to the original position when S0 and S1 exchange their positions. See, when I permute and come back, S0 and S1 are just set. That is why I told you this ordered pair versus unordered set. I have to sort of keep confusing them all the time. Okay, I started with S0, S1. At that point, I am thinking of them as just a pair of roots, but that's not enough. Now I put a blue mark on one guy, a red mark on the other fellow, and then I move. When I move, I come back. I bring S1 back, doesn't matter how. I just bring S1 back to S0 and S0 to S1 position. When I do that, then what happens is that these coefficients should sort of reflect the fact that the position has changed. But they don't, because they are continuous functions. Okay? So the theorem is therefore that there is no R0. Here I have written R0. You can think of R0 as a continuous function, such that is always a solution to the quadratic equation Pz equal to 0 of this form. This cannot happen. Everybody convinced with that? Very good. Now I think I have earned the right to get you all confused for the rest of the lecture, right? So this much I have also understood. Let me admit. Okay. Now okay, this is some kind of funny explanation. Again, as I said, I leave the slides behind if you want to ever take it. The picture actually does it, but there is a little explanation. Now comes, so in a way, understanding this, what happens from 2 to 3, 3 to 4 and 4 to 5. At this point, of course, if you didn't know, you would say, what the hell this guy is going to do? To go from 2 to 3, 3 to 4, 4 to 5, 5 to 6. Where are you going to stop? Fortunately, God is with you and not with me, so I cannot go on, and we have to stop at 5. Okay? So you don't be too impatient. All right. So what happens? Pz is this equation, which is a cubic, and now we assume we have a solution. But the hierarchy I was talking about, we now allow a square root to come in. Previously there was no square root. By the way, I should have made a remark that what we saw previously was that you cannot have a solution using only continuous functions. But then the question becomes, I mean, what else? Like I am saying here, add a square root, perhaps it works. Now, as log would have it, in the quadratic case, adding a quadratic does work. So you have nothing more to do. You back up and go home. Okay? Now, in the cubic case, similarly, and this is true of the quadratic also, that you show that you cannot do it with one level of nested radicals. But then you stop because you know that there is a formula that gives you the answer in terms of a second level of nesting. Same for quadratic. You show that 2 levels of nesting will not do it. But then there is a formula for 3 levels of nesting, and so you don't do anything. And then the fun starts when you go to the 5th degree equation. So I am not going to talk a lot more about this. By the way, the whole history about what these formulae were, how they were discovered, and so on and so forth, is quite interesting in itself. Okay, now coming back to a little math. We want to look at cubic. And we claim that this time there are 3 solutions, and each of these solutions, I say, can be expressed using R1 functions. R1 functions. Now these R1 functions are functions of the type, they are continuous functions, they are roots of continuous functions, and then they are combinations of the roots of continuous functions and continuous functions. Okay? So, one level of radicals. We still have that each coefficient as solutions permute, as solutions move around, if they come back, coefficients will come back to their original position. However, functions like R1 with radicals in them no longer follow a loop. So what is the basic difference between the quadratic and cubic? In the case of cubic now, because we have added a radical, think about the square root of g. Even if the roots are permuted, the thing is that these R1 functions don't really follow a loop. So they can perhaps reflect or capture the lack of loopiness in the solutions. Okay. So the idea is, because you have thrown in a loop, you don't have to worry about things not coming back to themselves, because the root function doesn't come back to itself. But is it enough? That is the question. So the thing is, before, remember I told you there were three terms that I used. There is a fourth term that will be coming. But the three terms that I used were permutations, loops, and two kinds of permutations, namely transpositions and cycles. Transpositions we have seen. Now comes the cycle. So consider the transposition 1, 2. So as I said, this square root or root kind of function doesn't have to have a loop. Okay, it will be a half loop, so to say. So what do we do to arrive at a contradiction? The idea is to arrive at a contradiction. So we consider a transposition and one loop. So this is a loop in R0. In the space of continuous functions, it is going to do nothing. Okay, it's a transposition, it will just be a loop. And an unclosed R1, when you are looking at square root functions, that's the whole point. Okay, when you are doing a transposition, that corresponds to, what does it correspond to? Like the square root of g, a circle goes to a half a circle, which means that is actually an unclosed path. Okay? So similarly, consider the transposition 2, 3, inducing a loop gamma 2. Again, on continuous functions, nothing will matter. Okay? But it will induce a half path, so to say, in the space of roots, square roots. So now you follow them one after the other. So the following sequence of transpositions, called the commutator of 1, 2 and 2, 3, and denoted by this, is going to be our new character. Okay, the new character is a commutator. Now since what 1, 2 inverse is 2, 1, 2, 3 inverse is 3, 2, it follows that this is a cycle 1, 2, 3. If you work it out. Again, I have done it. Those of you who want to write it down, follow through what happens to 1, 2, 3, and you will find that it is a cycle. Indeed, this is true of any transposition, that you will find that is so. Therefore, 1, 2, 2, 3 permute the three solutions. The idea is to obtain something. A cycle is actually permuting the three solutions. Now, R0 follows a sequence of loops. If you do this gamma 1, gamma 2, this is the commutator. Nothing much is going to happen because that's a continuous function and loop remains a loop. Okay? But R1 follows a sequence of unclosed paths. Omega 1 first, then omega 2, but then omega 1 inverse, omega 2 inverse. Visiting other roots, but closes on itself by construction. Now this is the part that I would like to demonstrate, what that means both in terms of pictures. So if you look at that, and hopefully I will succeed in demonstrating. Let's see. I was going to request for some contraption, like in magic, what do they do? It's called props. I was going to ask for some props, but that I didn't. Let's see. So I want to tell you what exactly is a. How many of you have seen this? Hopefully now this is okay. Hopefully it should work. public is that if you are not who you think you are, you mess up. But let's see. This is supposed to demonstrate what a commutator is. I'll tell you why and what. This is, again, if you go to the internet, you will find that there is a lot of talk about what is called a picture hanging puzzle. Imagine that these two hands are like two nails on which you are hanging a picture, like this purse here. And the puzzle is that you pull out one of the nails, then the picture should fall down, right? Now comes the moment of truth. So you can, if you don't believe me, I can try to do it again. But that's not the point. It worked at least once. Now I don't want to take a chance. But why does it work? Well, the commutator is AB followed by A inverse followed by B inverse. Now you pull out one nail, that means you pull out the B inverse and the B. If you pull out the B inverse and B, that were making AB, A inverse, B inverse, right? Pull out the B and B inverse, what is left is A inverse. That's identity. And that's not going to hold your framework. Okay? So commutators are just that. And here, if you again follow through the picture, you will find that we have created exactly that situation. And for the purpose of this counter example, it is enough to produce just one instance. I don't have to worry about every little permutation, every little path, and so on and so forth. All I am saying is that there is a permutation where the roots are moved and the function that was supposed to be tracking that root hasn't moved, and therefore there is a contradiction. Okay? So we have managed to go past one more hurdle. Now, as I said, at what point does it get to be boring? One more thing, and then we will be in use. So again, I have tried to write down this. Suppose that S1, S2, S3, I have demonstrated, can undergo a cyclic permutation, but both, while that happens, both R0 and R1, I told you follow a loop, because I can take the commutator and write it as two transpositions, and therefore this will follow a loop. Consequently, we can have equalities of this kind, because if I had an equality of this kind, S1 would have changed its position to S2 at the end of my term, whereas that R1 1, when I finish from 0 to 1, is not going to change. So you can't have a formula like that. Again, this involves only one level of nesting with radicals. The actual cubic formula sort of somehow tells you that, okay, it doesn't work with this, but it works when you do a double nesting. Two levels of nesting will do. Alright, we need to introduce one more idea again, commutator of commutators. Okay? What is commutator of commutators and why is it necessary? Now when you go to the quintic, you again face a new challenge. So you say, you have a quintic equation, assume that you have a solution of this form. Now R2 is obtained from the previous guys, R0, R1 type things, but now adding a further square. So you have two levels of nesting of roots. Okay? The proof consists of constructing an appropriate permutation of the solutions this, so that as before, solutions permute, but this function that tracks the solution does not change its position. Well, that is easily done by looking at, well, if you are Arnold, everything is easy. I have been struggling with this for last so many days and nights actually, trying to be a little honest that I have some idea about what is going on. Otherwise, so this is it's very important. But I think it's okay. So as before, like the method for quadratic did not work for the cubic, the method for the cubic doesn't really work for the quadratic. Okay? But then what do you have to do? Hunt for a new idea again. So before, from transpositions we came to cycles, and cycles provided a permutation of the roots. Now what we do is we look at a commutator of two cycles, and if we look at this particular 1, 2, 3, 2, 3, 4, and then the main point here is that you can take 1, 2, 3, 2, 3, 4 and write it as a product of transpositions. And that again does it. Because being a product of transpositions, you can argue that this particular commutator actually is a non-trivial permutation. Okay? It's a non-trivial permutation on the roots. And so applying this followed by this to functions of type R1 produces two closed loops again, coming back to the original loops. However, the functions of type R2 will move along to generally unclosed paths omega 1 and omega 2. Okay? But we apply these two paths backward. That is, we are doing a commutator of a commutator. So we do 4, 3, 2, which is 4, 3, 3, 2, and then 3, 2, 1, which is 3, 2, 2, 1. During these two, R1 functions will follow gamma 2, gamma 1 inverse, and therefore they will remain unchanged. The previous loops backwards. Similarly, R2 functions will now travel that unclosed path that we had by applying omega 2 inverse followed by omega 1 inverse. We make them closed. Thus R1 functions follow the loop this, and R2 functions a sequence of unclosed paths which closes on itself by construction. Okay, because this is this commutator of commutator that we have taken. Our conclusion has therefore been reached while S1, S2, S3, S4 undergoes the permutation list written as a commutator of commutators. Any R2 function follows a loop. Okay? So now comes the quintic. Alright. For the quintic, we say that we have a fifth degree equation, and following what is done in the case of 2, 3, 4, note that all RK functions with k equal to 0, 1, 2 will follow a loop from a commutator of commutators of this level. Okay? So that is the highest level that if you necessary to take that, as in the quantic case. But we will need one more level of commutators for additional root appearing in R4. So three levels of nesting are not enough. So, but the point is, if you want to pause for a second and think, of course the story cannot continue like this, because you know that the fifth degree equation doesn't have a solution to that. So if I could repeat that argument, then I will go on. But I can't, because what we are now going to say is we add one level of additional nesting. Well, that will fail. But what is more? If we add 2 levels of nesting, that will also fail. If we add 3 levels of nesting, that will also fail. Okay? Now for that,
sir, you have only allowed square roots and their nesting.
you are allowed.
You have allowed square roots and their nesting as valid operations. Like what about
that's what I said. Square root is the minimum that you need. If you are given a third root or seventh root, you are even better off. Okay? You have to think about that a little bit. But square root is the minimum that you need. But if you are allowed to play with third root and seventh root and 19th It's in the back. Okay, the same kind of contradiction can be easily used. Okay. So okay. So as I said, I want to first rule out this R3, and this should have been R3 actually. Additional root appearing in R3. Okay, but in general, however, the big difference is that in general, with n equal to 5, when you look at the permutations, now this is a special property of the permutation group. Now this is where the conclusion of the Galois theory and this proof sort of converge. Okay, this is a very, very special property of the permutation group at n equal to 5. So when n equal to 5, if you look at these cycles, the commutator of these cycles is again a cycle. But since this was practically arbitrary, you take any jkm, you can write them as commutators of ijkklm. What is surprising about that? Now I have been using the term nesting. What is interesting? And this is what makes mathematics so exciting, is that when you look at something like this, you observe that if this can be written as a commutator, the two entries inside the commutator can also be written as commutators themselves. And this process can go on. You don't have to stop. Once you have written them as commutators of cycles, whatever appears there, you write them again as commutators, right? So a cycle can continue to be nested as many times as you want by using these commutators of commutators of commutators of commutators. Okay? So, hence the cycle jkm can be written as a nested commutator of commutators as many times as you want. And I repeat, this is a special property of S5. This didn't happen in S4 or S3 or anywhere else. Now, this again, I am not going to say too much about this. If you imagine the way the proof went, when you have, this is sometimes called, what is it called? Breaking a loop or something. How did the proof by contradiction go so far? We had a permutation and we said that we also have a loop. Now to be able to get to that loop, what did we do? We said that, well, even if there are roots, we will use these commutators, we will use this transposition cycle, whatever, and we will break that nesting into a simple loop. Okay? That is how it was done. If you imagine the last one, at the fourth degree equation, we needed a commutator of a commutator. Why did we need a commutator of commutator? Because there were two levels of nesting and two degrees of taking commutators of commutators, so I was able to throw it out. Now here you have the luxury of commutator of as many times as you want. So what will happen is, no matter who gives you, not just the S3, no matter who gives you a S4, not S3, R3, no matter who gives you a R3, R4, R5 or R6, what does it mean? It means that there are such a large degree of nesting of the roots. But then you start with that many commutators, okay? And then what will happen is, those many commutators are going to still give you a permutation. They are going to give you a cycle. But that is exactly the point about S5 being solvable, okay? And then you will arrive at a contradiction that no matter what is the level of your nesting, you will always be able to find an appropriate loop, okay? That will sort of loop on itself, whereas you will have a permutation of the roots, giving you a contradiction. So there is no finite nesting that will do this. In fact, there was a question asked by someone on the internet, and someone answered the question also, although I have not been able to think about it. Namely, that if you allow infinite nesting, can you actually find a solution for the... And someone said, yes, you could, but I know that this proof doesn't work. But I don't see why the answer is yes. Okay? But that's what was on the internet. The internet is a dangerous place from that point of view. Anybody can walk in and say whatever they feel like, and you have no way of actually verifying what is what. Now, coming back to the 15-minute proof. So I started with telling you that there is this Galois thing that tells you, okay, to sum up what is being said, denote the space of coefficients, and you look at the space of solutions. Order these any way you like, which is not literally true as I have explained to you. We are not looking at an unordered set. Sometimes it is an ordered set, sometimes it is not. Okay? If you are thinking of it as a base point, it is a ordered set actually. Okay? And now we have seen that there is a map from the space of loops to the permutation group S5. Okay? And so as you move the coefficients around, you will see that, as I said, if there was internet, there is a beautiful Java applet somebody had made with two spaces like this, the space of coefficients and the space of solutions, and you can play with it to see exactly how when you move the roots around, how the coefficients move, and how when you move the coefficients around, the roots move. It is particularly interesting when you make the things move around the origin versus not moving around the origin. That's the point. Okay? So there is a map from the space of loops to the permutation group. This map takes a little while to think about it, but this map is a one-to. Given any permutation, you can actually find a loop in the space of polynomials. And this I am doing only for S1 through S5, meaning I am doing it for the 5th degree polynomials. I am thinking of all the 5th degree polynomials as my space of coefficients, minus those where there are double points. I throw those out. Now, why that is necessary is another question, but we don't have to worry about that too much. And the crux of the matter is that if you look at a loop, and this F is like your R function, okay? It's like a branch, or it's like a root, or something or the other. So if you have a loop, and that induces a cycle because this map is supposed to be onto, but then the whole crux of our argument has been, if you are looking at a root, nested or otherwise, that composed with this gamma will come back to gamma 1. That composed with gamma at 1 is the same as what it is at 0, comes back. Okay? After doing all this commutator or whatever. And on the other hand, it's actually a permutation. That's a comparison. That is supposed to be the 15-minute proof that this drawer, then Alan or somebody actually described in a classroom. So that's it. There are a lot of stuff, but there is a whole bunch of these things that I have listed here. I have taken much of it from here. This is actually an American Math Monthly article. This Ram Prasad Saptarshi talk that you will find on the YouTube is really, really very well done. I strongly recommend that you look at that. And then, they're kind of related things. Actually, it looks like to me, all of this started by this guy, Boaz Taj, who about 2-3 years ago put up a half-an-hour video saying that there is this Arnold's proof that can be seen in this way. Okay? And all right, so I'll stop there.
So
So as I move the coefficients around, please look at what is happening to the root minus 1. Alright? So I move it around like this. What happened to minus 1? Came back to plus 1, right? And that's the whole point. So if I do it again, see this is where I have held it now, somewhere in the middle of the path, right? Now I bring it back slowly, and then the minus 1 has become plus 1, and the plus 1 has become minus 1, right? You can do it with the number of roots increased and all that. But this is why, because you are talking about permutations, this, that, and the other, essential to this argument is the fact that you have distinct roots. I mean, if the roots coalesce or something, then you won't be able to get this argument. Okay. This is a beautiful argument, actually.
Are there other questions? Okay, so if not, let's thank Professor Misra again.
I finally survived this one.